everyone and welcome to my channel Ghiloo once again. So in this video we'll be continuing from question number 17 of exercise 5.1. So here it's a very simple question. We have a function and instead of trying to find whether it is continuous or not, we need to find the value of a and b where the definition breaks, and we have to show that this function is continuous for those values of a and b. That means that we need to make this function continuous at x equal to 3. So let's do it. First let us write the given function. Now if this function needs to be continuous at x equal to 3, then obviously LHL must be equal to RHL, and that must be equal to the value of function at 3. So that is what we are going to then write by words. Or now let us break the definitions. So for x less than 3, which is the case of LHL, we have it as limit of x tends to 3 minus f of x will be ax plus 1. So that will be giving us 3a plus 1. So similarly, limit of x tends to 3 plus, here the definition breaks to bx plus 3. So this is going to be equal to 3b plus 3. And finally, f of 3 is equal to a times 3 plus 1, that is equal to 3a plus 1. So obviously, as we can see very clearly, that 3a plus 1 must be equal to 3b plus 3. So if we divide the entire LHS and RHS by 3, we get a plus 1 by 3 is equal to b plus 3 by 3, which is 1. So that gives us a is equal to b plus 2 by 3. So that is the relationship between a and b, for which the given function will be continuous at x equal to 3. So you have to remember that you can put any a and you have to get a corresponding b, or you can put any b and you have to get corresponding a. Means they both should be related by this expression, and there can be infinite such values. Now coming to the next question. In the same way, we have question number 18 here. For what value of lambda is the function defined by this continuous at x equal to 0? What about continuity at x equal to 1? So since here the function breaks at 0, and for x greater than 0 the function is a polynomial function, so obviously it is continuous at x equal to 1. Let us now check it in a different way. So the given function is, if f is continuous at x equal to 0, the left hand limit and the right hand limit should be equal, and that should be equal to the value of the function at x equal to 0. So that is limit of x tends to 0 minus, so that gives us at the left hand side of 0 the function is defined like this: lambda of x square minus 2x, which is equal to limit of x tends to 0 plus 4x plus 1, which is equal to f of 0 means the value at 0, that is 0 square minus 2 into 0. So that gives us lambda times 0 square minus 2 into 0 is equal to 1. 4 into 0 plus 1 equal to 0. So that means that 0 is equal to 1 is equal to 0, which is not possible. So therefore we can clearly conclude that there is no value of lambda for which f is continuous at x equal to 0. So therefore I hope you have no trouble in this. Now moving on to the next question. Coming to question number 19, here we have a function that is defined by g of x is equal to x minus integer part of x. So we need to show that this is discontinuous at all the integral points. Means it is discontinuous for minus 3, minus 2, minus 1, 0, 1, 2, 3, and like that. Now for this we shall take a shortcut approach that would help the problem being solved very easily. We'll be having a graphical approach here. There are other approaches as well, but I shall stick to that here. Now given g of x is equal to x minus integral part of x. So if I remove integral part of x from a number, what I get is the fractional part of x. So we will be defining where represents the fractional part. So we can draw the graph of this fractional part, please observe it very closely. Since it is fractional, the value can only range from 0 to just less than 1, that means 0.999999 like that. Means it won't be 1. If it is 1, it becomes an integer. So this is 0, 1, 2, 3, 4 like that, and this is 1, 2 like that. Now since fractional part will never be 1 but will be just less than 1, we get one graph like this. Similarly from 1 to 2 we get a line like this. Similarly from 2 to 3 we get a line like this, because this only represents the fractional part, and that's how it goes. Alright, here we can clearly see that this is discontinuous at all the integer points. So from the graph, gx is discontinuous for all x belongs to integer. Alright, you can also do it in another way by assuming the LHL and the RHL. Okay, you can take any integer point. Let us say we take x is equal to n. So for x is equal to n plus we have something, for x is equal to n minus we have something. So both are not going to be equal. So LHL is not going to be equal to RHL, hence it is discontinuous. From the graph you can easily state that. Okay, now coming to the next question. So a function here, and once again, is it continuous at x equal to pi? Let's check. So the given function is, we need to check whether it is continuous at x equal to pi or not. Let us use a short trick for this. Now let hx is equal to x square plus 5 and let p of x is equal to sin x. Okay, now we know that any polynomial function is continuous. Also sin x is continuous throughout its domain. We know both of this information, alright? So hence hx and px are continuous. Now we have learnt a property in this chapter which says that if f of x and g of x are both continuous, then f of x plus g of x or f of x minus g of x must be continuous. So we'll be using this property here. Hence h of x and p of x are continuous. Therefore by the property h of x minus p of x is also continuous. But h of x minus p of x is equal to x square plus 5 minus sin x, which is equal to f of x. So therefore f of x is continuous at x equal to pi, because it is continuous for all x belongs to the real number. So this was a shortcut way. You can use this because this has been taught to us. So I think you have no problem up to this. Enjoy, like, share, comment. We'll be meeting in the next video. Thank you very much for watching this video.